Please go ahead.
Okay. So, thank you for the presentation of myself. And I work with Guillaume Jomeret at Mathieu Saland at in our lab. So it is a very great pleasure for me to have this chance to present you my work during the DFT days. Okay. So redox reaction is one of the fundamental chemical reactions, and electron transfer is the central idea of a redox reaction. And the solvent plays a very important role in an electron transfer. So here I would like to use a simple schematic representation of this chlorine minus chlorine redox half reaction in water to show you the effect, the role of solvent in an electron transfer. So first, we are in equilibrium here, where chlorine minus in equilibrium with water. And if we take an electron from chlorine ion to obtain an chlorine atom while keeping the solvent unchanged, we will raise the free energy of the system. And then we need to let the solvent to reorganize to accommodate the chlorine atom. And then we will, again, in another equilibrium. So we can trace this reaction path. We can trace the free energy with respect to the solvent configuration here. So at the beginning, we are at this point, the minimum of one free energy curve. And once the electron transition happens, we vertically raise the free energy to this point because the solvent configuration are freezed here. And then we follow this black curve down to the minimum here. And while letting the solvent to reorganize. And with this simple demonstration, there are 2 points to remember. First, movements in x-axis means that we are reorganizing solvent. And secondly, on each curve, electronic state is unchanged. And we call these kind of curves free energy profiles. From free energy profile, we can define several important parameters. The reaction free energy, delta G, which is the free energy difference between two equilibrium solutions. The activation free energy is the reaction barrier. And the solvent reorganization free energy is actually the free energy difference between the step 2 and step 3 that I've shown before. And we can relate reaction free energy and activation free energy to the redox potential and the reaction rate constant of a redox reaction, respectively. And solvent reorganization free energy can be used to relate them. So we know that free energy profile is a useful tool to help us understand the thermodynamics and the kinetics of a redox reaction. The problem is, how do we construct free energy profile by classical DFT? And before going into detail, I would like to emphasize that within a classical regime, we only look at solvation effects. And to have a precise calculation of reaction-free energy, we need very precise, very accurate quantum mechanical calculation. So now we are going to construct these free energy profiles with solvation free energy as y-axis with classical DFT. So first, we start with simple points. We calculate two equilibrium solutions, which are present here with filled circles. And then we need to explore other solvent configurations. And because in classical DFT, we have this one-to-one relationship between external potential, equilibrium density, and minimized free energy functional. So we can interpolate the external potential of these two equilibrium solutions. And then we can obtain this series of equilibrium solvent configurations. Okay, and then we need to evaluate out of equilibrium solvation free energy of the two solutes, 0 and 1, solvated in these intermediate equilibrium solvent configuration. And it should be mentioned that these solvation free energy are out of equilibrium. And we don't do a functional minimization at this step. And finally, we need to have a simple parameter that can represent solvent configuration and can be quantified. And in our recent paper here, we have shown a one-to-one relationship between the interpolation factor eta, the interpolated external potential, the intermediate equilibrium solvent configuration, and the vertical energy gap, which is defined here. So in our study, I'm going to use the molecular density functional theory to calculate the solvation free energy. So from the Evans paper and the theory of simple liquid, we can derive an expression for the grain canonical potential. And if we take the difference of grain canonical potential of the state that we are interested in and the homogeneous bulk fluid, we can also derive an expression for the free energy functionals. And it can be divided into 3 parts. So MDFT is dedicated to study the solvation problem. That makes MDFT a very useful tool to construct free energy profile. So in MDFT, the particle density describes the solvent density. And we can simply generalize the dependency of solvent density on not only the space coordinate, but also the orientation of solvent molecule. And here is a schematic representation of how we determine the orientation of a water solvent molecule. So in MDFT, we also have this one-to-one relationship between external potential generated by the solute and the equilibrium solvent density and minimized free energy functional. So we can obtain minimized free energy functional at equilibrium solvent configuration by minimizing the free energy functional with respect to solvent density. And the minimized free energy functional is exactly the solvation free energy. So now we can write down the expression for these 3 parts of free energy functional. The ideal part, we can calculate it analytically. And the external part, it depends on the solute-solvent interaction in principle, but we can also introduce some hard walls or electrostatic field to influence the solvent density. And the excess free energy functional can be further divided into 2 parts. We collect third and other higher order free energy functional term together, and we call them bridge functional. And the second order is written here with a 2-body direct correlation function of homogeneous bulk fluid as a key parameter here. But it is not easy. It is still not easy to calculate the second order functional because this direct correlation function is not easy to calculate. We need to ask help for the molecular simulation. And even once we have this object, how can we calculate this integral efficiently? And Dean et al. Have proposed a method to calculate this integral efficiently by using generalized spherical harmonics expansion. And the details can be found in this paper. And beyond this second order, the bridge functional is even more complicated. So the simplest approximation is just to say that bridge functional equals to 0. And actually, this is equivalent to the hypernetted chain approximation. But we all know that truncating functional at second order is not so good. it will result in an overestimation of free energy per molecule at zero density limit. And because we are studying solvation problem, when we introduce the solute inside the solvent, the solute will exclude a volume. And the free energy of forming this cavity inside the solute will be overestimated due to this error. So there are two general strategies to correct this error. The simpler one tries to estimate the volume excluded by the solute, and then just subtract an amount of free energy from the calculated solvation free energy. However, this kind of approach won't modify the equilibrium solvent density, and we call this kind of strategy a posteriori correction. For an example, we take the partial model volume correction proposed by Sergivsky et al. to be an example, and this correction method is also adopted in the theory of RISM, reference interaction site model. The other strategy is to propose some form of bridge functional to recover some characteristics of third and higher order functional terms. And we call this strategy correction at functional level. And we take the bridge functional proposed by Borges et al. As our example. So let's see how this correction will influence the construction of free energy profile. And here we take a chlorine plus chlorine redox half reaction as an example here. So for every intermediate equilibrium solvent configurations, we have a corresponding partial molar volume correction value. And this value is actually the same for both curves. So let's take a closer look here of free energy profile of chlorine plus iron. We can see that upon applying PMV correction, the minimum of the free energy profile is shifted a little bit. However, this is a big problem because if we think in a reverse way, the minimum corresponds to another vertical energy gap, meaning that the minimum corresponds no longer to the equilibrium, no longer to the solvent configuration that is in equilibrium with chlorine plus iron. And this violates variational principle. This can be better illustrated by plotting solvation free energy with respect to the interpolation factor eta. When eta equals to 0, represent the equilibrium solution of chlorine atom. And when eta equals to 1 indicates the equilibrium solution of chlorine plus iron. So we can see that upon applying PMV correction, the minimum no longer correspond to the equilibrium solution. And again, it violates variational principle. We can also plot the PMV correction value with respect to interpolation factor. We can see here that the minimum is sit at around eta equals to 0.56, which means that the states other than equilibrium solutions might have lower free energy upon adding PMV correction value to its solvation free energy. And the shift in minimum also affects the determination of solvent reorganization free energy. Here is a set of lambda value calculated with mathematical definition shown here. And if we calculate the lambda with directly on the free energy profile, we will obtain another set of value. But in principle, these two definitions are equivalent to each other. So again, we claim that it is inappropriate to apply a posteriori corrections in the construction of free energy profiles of an electron transfer. On the other hand, theoretically, we can avoid this problem by doing correction at the functional level, because the correction is directly incorporated in the determination of this series of equilibrium solvent configurations. But at the first glance, we may also ask why, again, this minima has different value of exposition. But it should be mentioned that upon considering bridge functional, we have different equilibrium solvent configuration. Thus, we will have a different vertical energy gap. And we have verified that these two new minimum correspond strictly to the equilibrium solutions. So in summary, applying a posterior correction could result in violation of a variational principle and the inconsistency of definition of reorganization free energy in the study of electron transfer. But we can avoid this problem by doing correction at functional level. And the detailed discussion about the detailed discussion can be found here in our new recent paper. So thank you for your attention.
Thank you very much, Suyao, for this very nice presentation and compact presentation of very complex theoretical calculations indeed. If I may ask a question immediately, and it's a basic